Recently, there's been a lot of talk about C++26 because the standard now adds compile time reflections. Unfortunately, only our grandchildren will be able to use them. Hell, I'm still waiting for C++20 modules. But thankfully, recently I've discovered a language called D. D is a pretty direct successor to C++, made by Walter Bright. It's a language that has had compile time reflections for a very long time, and many more nice features. So today, let's take a look at the language and see why maybe you might want to use it for your next programming project. Okay, let's start with our example. We have our little structure, player data, and with a field of score, name, and a secret data. And over here, we're initializing it with 20 and John. So we can actually right away just print it out. And if you run it, ta-da, it prints just fine, because D actually makes use of its own reflections, quite nice. But let's say we want to actually reflect on it manually. So over here we define the little function reflect print. This might look a bit confusing, but this is how you define template parameters in D. Now, we've written a for each statement. This is a range-based for loop in D. The syntax can be a bit weird at first. Every struct and class has a property called tupleOf. This essentially gets all of the fields of the struct or class as a tuple, which is very nice. And we've made another change. We add a new symbol here. This binds to the current index. And using the actual type itself, we can get a tupleOf once again. If you use tupleOf on a type, it will get the names of the fields rather than the field itself. And using stringof, we can stringify it. And using an enum basically makes this just be a compile time constant. And we can print it out. As we see, score 20, name John, secret data false. Ta-da! Works quite nice. And let's just add the type in there as well. And ta-da! The type is there. We actually took this as a const object, so this is also gets printed out as a const. We can just remove this to get rid of that const, and ta-da! Yes, and it just works quite nicely. But we don't want to reflect secret data because it's private. Okay, let's do that. Okay, now we've made some changes. Now, field name is just the name of the field. It doesn't actually have any data associated with that field. You can use getMember to get this specific member of type T by the field name of field name. And ta-da, we can alias this into member. And we can also do the same thing, but for get visibility. And this static before the if statement basically just says this is not compile time. And if we run it, secret data is no longer being printed. Beautiful. Now, we don't always want to export every field just because it's public. Let's say you're writing an editor and you want to only export stuff with a certain attribute. Well, D actually does have user-defined attribute, just like C#. So let's say I only want to export score, or actually better yet, let's just say name. So I can just be like export, ta-da! And yes, any type can actually be an attribute, even an integer or a string, which is quite nice. And in our code, we've added this for loop here. Using traits, once again, we can get all the attributes of member, and we can check at compile time if this attribute is export. And yes, we can use stuff in any order of definition. This is a modern language. And only now we're outputting it. So if you run this one again, ta-da, only John is being exported. And all of this just works. Now, taking a look at a much simpler example, and this is probably what I should have started with anyway, just a simple hello world program. As you can see, we have this import statement, import stdio, and then we can just use writeLine without any namespaces or whatever. And modules in D are, in my opinion, the best module system I've ever seen. In fact, any language designer should just look at D and just copy paste it. The way modules work is every folder is a package, and every file in that that folder is a module, and that just works quite nicely. There's a lot more stuff to it than what I just mentioned, but yeah, this is a good introduction. One thing I quite love about modules is you can actually do imports in any scope, anywhere. So if I only want write line inside of main, I can do that. And if we run this, tada, hello world. But what if I have my own little write line function? Now, what if these two conflict? Okay, I can actually just do a selective import for write line and alias it as std write line. And again, it just works. This is just such a joy to work with. But what if I actually want to use std.io every time I want to use write line instead? Well, we can just make the import static. And now, if I just try to, let's also get rid of this. If I just try to write line, the compiler should complain. Yeah, it does. Write line is not user defined. It even tells us which module we need, which is quite nice. Yeah, now to make it work, we actually have to prefix it with std.stdio, just like you would in other languages. And ta-da, now it works. We could also do this. Yeah, so instead of writing that long module name, we can just use IO. You can do whichever is most comfortable for you. But personally, I think it's extremely nice not to have long namespaces or prefixes behind every function and class. This genuinely makes code a lot more readable. And because imports can be in any scope, name collisions actually don't happen that often. And when they do, you can just add a custom alias for it. Now let's take a look at another example. Over here, we're actually importing from the C standard library, and we're using malloc. Now D actually does have garbage collection, but it's extremely optional, and you can just use the C standard library to basically do everything. And yeah, over here we're allocating an integer, setting it to 20, and then freeing it. But this isn't great because if we leave the scope early, then it won't get freed, and that's a memory leak. But D actually has a great feature called scope guards. As you can see, we've written this code to use this little statement here. It says on exit, call this function, call this expression. This can also be inside of its own block as well. And yeah, at the end, it will just free this. And this just works quite nice. This is very similar to defer in a language like Go or Odin or whatever. And D actually does support RAII. But if you want to write code procedurally, you can just rely on scope exits. Now over here we have a struct called type wrapper. It basically just wraps a specific type. Now you might be like, when would you need to actually do this? Well, let's say you're making a optional, like std optional or a smart pointer, where you might have to wrap a type. And yeah, over here we have type wrapper, and we can directly specify what the template parameter is with int, and then yeah, value ++ and write line. And if you run it, ta-da! But this isn't great. We can do one better. D has a feature called alias this. Essentially, for any member you use this on, this type will be treated as if it's that member. It will alias itself as this member. So now, instead of using value ++, we can just use myInt ++. And we can also do write line on myInt, and it should just be an int. And if we run it, ta-da! We just print 1, and we incremented 1. For all intents and purposes, this type wrapper is now an int. And like I said, this is extremely useful when you're writing wrapper types like an optional or a smart pointer or anything else. This genuinely cuts down on boilerplate so much. It's an amazing feature. Now, D doesn't actually have support for preprocessors or macro functions, but it does have a very nice feature that actually basically eliminates all need for macro functions, and it's called mixins. Now, over here, we've defined a mixin template called adder with the template parameter of t. Wherever we use this on, such as here, in the global scope, we essentially just copy paste this with the type of int into that scope. We can also use it in the local scope because D actually does support local functions. But for now, let's leave it in the global scope. And if we run this, we get 15 because it has injected this function. We can also add one for floats. But if we run this, we get an error. We can fix this with some magic. Now, this might look a bit scary as opposed to what we had before, but bear with me. Instead of the single template parameter, we have something that's equivalent to C++'s parameter packs. Basically, just any number of types can be accepted now. And at compile time, we can loop over these types, which is something C++ cannot do. And for each type, we are doing something called a mixin. A mixin basically allows you to use any string to write the code. And at compile time, D will take that string and will attempt to compile it where you wrote the mixin. So, keeping that in mind, we define a function with the return type of T, add, and at compile time, we're concatenating it with, we get the type name of T, get a slice to the first element, and make it uppercase. And yes, we can manipulate strings at compile time, and it just works. There's no special keywords you need to use, it just works. And then we concatenate it with the rest of the string. This $sign basically means the length of the size of the string, right? It's basically like the last array element. And then we just write the rest of the body as a string. And at compile time, for every type you give this template mixin, D will take that and generate this bit of code. And yeah, we have int and float. So now we have add int and add float. And if we run this, it just works. Now, whenever I see a feature like this, I would just think, yeah, that looks nice, but it probably is very error prone and doesn't work that often. But in my experience, this often just works. And when it doesn't, the errors D gives you are actually readable. You can actually understand why it doesn't work. Now let's take a look at multi-threading. Over here we have a global counter called gcounter. Now this keyword here, gshared, basically means this is shared across all threads. By default, if you define a global as static, this will actually make it thread local by default, which is very nice. But for the purposes of this example, we're going to keep it as gshared. And inside of the main function, we have this nice little range expression for the for each. And yeah, we're spawning 4 worker threads to count to 60. As you can see, we're incrementing this without any synchronization. Now, of course, you would make this in atomic, but for the purposes of this example, let's not use atomics. D has a statement called synchronized. Basically, any expression afterwards will be synchronized. It's literally built-in synchronization, and this also works for code blocks as well. These are two really nice features of D I quite like. So let's take a look at this vector implementation that I quickly spun up. I think this is a great case study of why D is such a great programming language, especially for game development. So over here I have a vector implementation, and this is like the mathematical vector, not the dynamically sized array kind of vector. It takes 2 template parameters, a base type and the total size of the components. And over here we have a constraint that is a real type. We create an alias here just to make it easy to reference the type. Now this is quite a standard way to implement a vector, or else I think it is. You have an anonymous union with 2 members, a struct and just the raw memory. This way you can access it by like x, y, z, w, and also the underlying array. This also makes it very useful for doing interop. Now in the constructor, I don't have a specific constructor for like different arrangements. It just has just one parameter pack. Just does a quick assertion and then just does a compile time for loop to set all of the elements. Nice and easy. Now the place where this really shines is in the operator overloading. The way in D In D, if you want to overload an operator, you just implement one of these functions, built-in functions like toString, opBinary, so on and so on. So yeah, we have opBinary for obviously binary operations, and we use the mixin we saw earlier to achieve this. This is the actual code. Just put the op here, because compile time string, it just works, right? It's actually a template parameter, and if we want, we can actually put constraint on which operators are allowed. So over here in the unary, we just say if it's a negative unary, then if it's a negation, this should work. Otherwise, it'll throw an error. Yeah, and that just works. And you might see these brackets here. D actually has built-in array programming, and this will very likely compile down to SIMD instructions, and that just works. And actually, I benchmarked it against SIMD code, like using SIMD intrinsics, and it actually gave me better performance. So it's probably doing some optimize. I mean, I'm pretty trash at using SIMD, so take that into account. But yes, obviously applying the correct optimizations. And you also have the scalar version, and of course the op-assign versions. And yeah, and of course a little toString function just uses the raw, and all the operations you would expect from a vector. I did not implement cross product, but yeah, it's good enough. As we can see in the main function, it's a little example. We have vec A, vec B, and then we just add them up. Nice and easy. And if we run it, ta-da, it just works. And this is being vectorized into SIMD. Quite nice. As you can see from all the features we've looked at so far, these are very pragmatic programming language. It's very focused on reducing boilerplate. Like the mixins genuinely help so much to reduce boilerplate. I only have to implement the binary operator just once, and it just works. Of course, in C++ I could just write a macro and then just copy paste it a bunch of times, but macros are terrible. In this is just a plain old D functions, and it just works. It's beautiful. It's easy to put constraints on what can and can't work. This just works, unlike macros, which are a great way to write bugs. Now, despite all of these great strengths, it does also have some major flaws. One of the most important being that it has a garbage collector. Now, D's garbage collector is completely optional, and you can actually turn it off just fine. And you can even use an attribute to make an entire scope not be able to use a GC, which is extremely nice. But the problem is, certain parts of the language are designed in mind for using a GC. In fact, the entire standard library is built with the idea of that you will be using a GC. Structs and classes have a very important distinction, that structs are value types and classes are reference types. If you're familiar with C#, you would know how this works. As a result, classes cannot easily be on the stack. They can actually be on the stack. You can allocate classes on the stack using the scoped function, which is a template. This makes heavy use of alias this, but it still is a different object. You can actually cast it to test to make it that object. Yeah, you have a class on the stack, and if you're not, it works just fine. You don't have to actually use the GC. But I still find this quite clunky to work with, and I wish I could just have this as a first party thing. In my opinion, D should have never had the garbage collector to begin with, or it should have been opt-in instead of the default. Because I found working with classes and structs becomes a bit overly clunky as a result of this. For example, because classes are reference types, when you try to construct it manually using the inplace function, it returns the class itself, because the class is a reference type. It's essentially just a pointer to the actual object. But if you use inplace with a struct, it returns a pointer. So you have to account for this and have, if you want to make an object that allocates, creates a new object, you have to have two versions of it, one for a struct, one for a class, and that's quite annoying to work with. But that actually might be the only gripe I have with the language itself. I have built an entire allocator for my game engine, and I found that managing objects and their lifetimes in D and completely sidestepping the GC is perfectly possible. I basically don't make any use of the GC at all, and you can actually make the compiler warn you about any GC allocations, so you can just completely root it out. So I would say the GC is in no way a deal breaker and can just be completely avoided. One nice thing about D is you can actually implement your own GC and make the application use that instead. So you can actually just like write a time slice GC like the one Unity uses, and basically make your gameplay code use a GC and the rest of the code be manually managed, which actually makes it especially ideal for game development. So both your scripting and engine language can be the same thing. It's actually kind of amazing. So while this is both a downside, I would say it also can be a positive as well, depending on how you look at it. Aside from the actual language itself, the issues really come from its ecosystem and tooling. Now the D compilers are amazing. There's 3 compilers: the DMD compiler, which I've been using throughout this video, which is extremely fast. I managed to compile a game engine, I believe it's called Dagon, which is around like I think 30,000 lines of code. With a fresh build, it took like a few seconds. It's amazing. But if you want to do a release build, there's LDC2, which does extreme optimizations and gets it pretty close to C++ performance. Of course, you have DOP, which is sort of a project management software slash build system. I'm not sure how to exactly describe it, but it's quite amazing. The real issues really come from the IDE support. Now, if you're someone that doesn't care about IDEs, then it's fine, it doesn't matter. But in my experience, all the IDEs I've tried with D kinda suck. The VS Code extension just doesn't work most of the times. I've only found that it like works 10% of the times, and even stuff like renaming isn't supported. Maybe it's a skill issue on my part, I don't know. And there's also an IDE specifically for D called Dext. It's pretty terrible. I wouldn't recommend using it. IntelliJ also has an extension. I found that one actually works pretty well, but IntelliJ kind of sucks. It's slow and bloated, but it works well enough. If you have access to it, then I recommend using it. And throughout this video, I've actually been using Z. The Z extension, I would say, is the middle point. Renaming works somewhat well. Okay, this time it didn't work. Great. But yeah, all of the language servers work okay enough. You got completing. Actually, where's my? Oh, okay, you don't have autocompleting because because this returns a alias this type, so it's actually a scope that it can't recognize that. It's a bit of a headache, but it's good enough for my purposes. But yeah, if you're used to more heavy-duty IDE support, then your D might fall short. Another thing is its ecosystem isn't great. Usually, if by some miracle a library you want exists, it's probably been abandoned for 10 years, and even when it was being maintained, probably wasn't that good to begin with. But the good news is C exists, and it is extraordinarily easy to create bindings for C libraries in D. There's a tool called DStep, which automatically generates a D module from any C header. And using that, you can just automatically create bindings for basically any C library. In a span of a few minutes, I created a working binding to the Jolt physics library using the Jolt C bindings, and it just worked. I just ran DStep on the header, and ta-da, it works. And I also did the same for a few different C libraries. So as long as there's a C library that does what you want, which most of the times there will be, then these ecosystems not being great probably won't matter that much.